Thank you for coming to my virtual poster presentation. My name is Daniel Fabian and I work in R&D of Lonza Biologics. My poster is about relatively recent work on the development of a deep learning model to predict antibody properties. So why is this important, you might be asking? So to optimize the manufacturing of antibodies, it is usually required to know the biochemical properties, such as aggregation or viscosity and other properties. However, this property assessment is often done quite late in the production pipeline, and it also requires tedious lab experiments. One solution to reduce the cost and time to production is to obtain a priori computational predictions of properties just based on an amino acid sequence input alone, which can be achieved using deep learning. So we have therefore created a neural network trained on numerical representations of 48 million amino acid sequences from UniProt, and then fine-tuned this model by further training it on 600,000 antibody sequences, most of which we obtained from public databases. Upon an antibody sequence input, our deep learning model generates a vector of numbers, so-called embeddings, representing its fundamental features. For instance, in the top figure here, we used our deep learning model to obtain sequence embeddings of thousands of heavy chain and kappa and lambda light chains of antibodies and cluster them using PCA. What you can clearly see is that the embeddings cluster by chain type, confirming that the model is able to differentiate between heavy and light chain types. So next, to predict the biochemical properties of antibodies, we built a top model associating property measurements from IgG antibodies with these refined sequence embeddings, testing several machine learning models. Our final top model is therefore able to take an antibody sequence as input and give a prediction for property as output. To give an example, in the middle figure here, we tested the performance through cross-validation R-squared values that you can see on the y-axis, so the performance of our model. And as you can see, those R-squared values indicate that we have achieved quite accurate top model predictions of several, in this case, computationally obtained IgG properties. What you can also see is that the figure shows that the predictions become better with an increased training data set. On the other hand, in the bottom figure, here we illustrating the model performance upon training on IgG aggregation, which was measured in the lab. Again, the R-squared values, as you can see on the y-axis, which we used to test the model performance, improved with increasing sample size. Okay, so to sum up our work, our model learned to accurately predict biochemical IgG properties just from an amino acid sequence input alone, but more complex IgG properties, such as aggregation, require a large training data size. In conclusion, our deep learning approach facilitates experiment-free quantification of antibody properties. Thank you again for your interest in our work, and if you have any questions or feedback, Please feel free to reach out to me.